This is Appendix D, page 2. Let's continue with graphing. The first sentence there says, forming the mirror image of a graph across a line is called reflecting the graph across the line. So let's graph each function. We've already graphed f of x is equal to the square root of x, and I will draw the table again here. We let x be 0, 1, and 4. If we take the square root of 0, it's 0, square root of 1 is 1, and square root of 4 is 2. We plot the points. And draw the graph. Now, do you see how there's a negative in front of the square root of x? So that means if I plug in the same values as I did in the previous problem for x, the only difference in the y's is that they're going to be negative. Well, 0 is never negative, so that's just 0. And instead of 1, it's negative 1. Instead of 2, it's negative 2. We plot these points. Do you see how for this one, if we compare the two graphs, this one is a reflection of the original graph, and it's reflected across the x-axis. Now let's see what happens if the negative is inside the radical. If I want to keep the original y's of 0, 1, and 2, do you see how we need to make the x's negative, except for 0? So negative 0 is just 0. If we wanted to find the square root of a negative something gives us 1, well, that would have to be negative 1. And then the square root of negative 4 would give us 2. And let's plot these points. And you can see that this graph, if you compare it to the original graph, is a reflection across the y-axis. So reflecting across an axis, if we have a negative in front, so that's in this case, see how there's a negative in front of the radical? Then, and here we have a negative f of x. Then if we compare the two graphs, you see how this is a reflection across the x-axis, if you compare the first graph with the second graph. So if the point xy lies on the original graph, then the point x negative y lies on the reflection. If we compare that one with this one here, y is equal to f of negative x, that's just like the third example. Do you see how we're comparing that with the first graph, how it's a reflection across the y-axis? So if the point xy lies in the original graph, then the point negative x positive y lies on this reflection. The graph, going down to symmetry with respect to an axis. So the graph of an equation is symmetric with respect to the y-axis if the replacement of x with negative x results in an equivalent equation. Or the graph of the equation is symmetric with respect to the x-axis if we can replace y with negative y and we get an equivalent equation. With respect to is kind of a common phrase, and so often we use WRT for this, and you'll see this later on when we're working problems. Okay, example 3. If we want to test for symmetry without seeing what the graph looks like, but just looking at the equation, we can do that. For the first one, if I want to test for symmetry with respect to the y-axis, I just replace the x with negative x. Now, does this result in an equivalent equation? Are these two equations the same? No. Now to test if it's symmetric with respect to the x-axis, I replace y with negative y. Let's try that. Well, if we have a negative inside the radical, that just is the same thing as the positive, and we can see that results in an equivalent equation. And so this is yes. The answer is it's symmetric with respect to the x-axis. So I'm going to write this symmetric with respect to the y-axis. The x-axis. Oh. Okay, so here when we replace the y with negative y, you can see that we found that it is symmetric with respect to So in the second part here, we checked for symmetry with respect to the x-axis, and you can see that this is an equivalent equation, the first one, and so this is symmetric with respect to the x-axis. Let's try part B. Let's replace the x with negative x. Well, if I have a negative number in the absolute value, it's the same thing as the absolute value of a positive number. And is that equivalent to the original equation? And yes, it is. This is yes. Now let's replace y with negative y and see what we get. And this is not the equivalent to the first equation there that was given, and so this is no. So the answer to this one is symmetric with respect to the y-axis, because when we replace the x with negative x, we got an equivalent equation. The next one, let's replace x with negative x. And 2 times negative x is negative 2x. Is this equation that I just wrote equivalent to the original equation? No. So it is not symmetric with respect to the y-axis. Now let's check for the x. Replacing the y with negative y. Well, we have 2 negatives, so this is plus y. Is this equivalent to the original equation? No. So this is not symmetric with either the x or and the y-axis, so I'll just put not symmetric. And then the last one, let's replace the x with negative x. Well, when you square a number, it's the same thing as squaring the opposite of it, so that's the same thing as x squared. Or you can see that if you square a negative, it becomes positive. So this is yes. This is equivalent to the original equation. And let's check the y also. So now I'm testing to see if it's symmetric with respect to the x-axis, replacing the y with negative y. And you can see negative squared is also positive, so we have x squared plus y squared is equal to 25, and this is also yes. So this one is symmetric with respect to both the x and the y-axis. So in general, the graph of an equation is symmetric with respect. Oh, okay. So now testing with respect testing for symmetry with respect to the origin, you replace both the x with negative x and the y with negative y. And if you have a result that is an equivalent equation, then it is symmetric with respect to the origin. So let's look at the next 2 examples. To determine that, we're going to replace both the x and the y. So if I replace both the x and the y with negative x and negative y, then we'll have negative y is equal to, here we're going to have 4 negatives total, which makes a positive 4x cubed. And then if I divide both sides by a negative 1, then we will have an equivalent equation. It's just like the first one. And so this is symmetric with respect to the origin. And then for part B, if I replace both the x and the y with negative x and negative y, we'll have negative 4, and then this becomes a positive x squared because it's two negatives. I could, again, divide both sides by negative 1. So we have y is equal to 4x squared. This is not the same as the original equation, and so this is not symmetric with respect to the origin.